section 2.4, implicit differentiation. So the idea of implicit differentiation is we are going to learn how to differentiate wisely. So let me first give you the idea of implicit and explicit functions. So most of the time we are going to get the function in the form y equal to fx. This thing is called explicit form. We call explicit form because, you know, y is on the left hand side and you have y equal to some function of x. So it is easy to understand, and you know, x and y are separated on each side, so you don't have to be worried about the confounding or something. So sometimes you're gonna see the function in the form fxy equal to c. Well, the problem here is on the left hand side, you're gonna have a function that contains both x and y. For example, you could have the situation like equation 1, equation 2, and equation 3. Well, luckily for case number 1, you can simplify and actually you get y equal to 1 minus 2x, right? I mean, if you move anything that related to x to the right hand side, so easy, so you get y equal to 1 minus 2x, and then now you can differentiate it, so you get minus 2, done. Well, easy. Well, case number 2 is a little bit harder because, well, you can say, hey, I can do y squared equal to 9 minus x squared. But anyway, y is equal to plus or minus square root 9 minus x squared. Well, I also can differentiate this thing, and the answer, it depends on the sign that I have, plus or minus, right? Well, but if prefer, I would not try to simplify this thing. Well, we will learn how to differentiate this thing by using another method. So we're not going to simplify the equation into the form y equal to fx. We are going to learn how to differentiate from the implicit form. So the thing that you see that I highlight in green now, this is called implicit form. So we're gonna learn how to differentiate by just, you know, looking at the implicit form. You don't have to simplify to the explicit form. For example, the equation number 3, it seems like you cannot simplify into y equal to something in terms of x because it's going to be messy and, you know, it's going to be super hard to differentiate. All right, so let's look at how we do implicit differentiation. All right, we have 32 students. Good. All right, so that is the definition of explicit and implicit functions. So I'm going to skip that part and let you read it by yourself. So we are going to look at the practice now. So let y be the function of x. Well, I would love to check if you understand this thing or not. So let's answer this is true or false. So the first one is easy. So differentiate x squared equal to 2x. For sure, yes, right? Because we have the formula, and if you differentiate x to the n, you get nx to the n minus 1. Well, what if I have differentiate y squared with respect to x? You have to be careful here because take a look, y is a function of x. Well, that means inside y, you still have x inside there because y is a function of x. When you differentiate y with respect to x, well, what happened is, because y is a function of x, so when you differentiate y squared, so by the chain rule, you're gonna have to times y, right? But your y is not independent of x, so you have to differentiate y one more time and attach it, because this is by the chain rule, right? Because you know y is a function of x. Think of y equal to fx. How could you differentiate fx square? That means you get 2 times fx, and then you have to differentiate inner function, right? So the same thing with this thing. So the key point is, if you see y here, so you need to apply the chain rule and have dy by dx attached with it. So sometimes you can make notation cleaner by saying this is 2y times y prime. Same thing, right? So this equation is false. So number 3, differentiate y cubed. So here you can get 3y squared, which is good, and then attach y prime. Perfect, right? Because by the chain rule, you need to attach y prime as well. So let me give you a quiz as a check-in for today. So tell me, do you think that this equation is true or false? In the chat, please. As a check-in for today, in the chat, type true or false. So I want to know, differentiate the product xy with respect to x, true or false? Well, Kittipat is the first one. He answered true, and Napatra is true. Okay. Seem like majority gonna answer true. I think I want to see who is the first one who answered false. Oh yes, we have Harisarut. Yeah, answer false. Good. All right. So let's look at this one. Is it true or false? So we want to differentiate x, y, right? So here, because y is also a function of x, you have to use the product rule, right? So it's gonna be x dy by dx, and then plus y dx by dx, which is very simple, right? And then you have x y prime plus y times 1, right? Which is going to be x y prime plus y. So good, this is true. All right, sounds good. Well, keep in mind that for implicit differentiation, it is not hard at all. The thing is that you need to be careful on each step, because sometimes when you differentiate y, you just forgot how to, you forgot that y is a function of x, and you forgot to attach your y prime in the equation. So we're gonna look at 2 examples to just practice about this topic. All right, so let's start by example 45. So this is the easy one. So an asteroid is a particular mathematical curve in the picture, well, which is used a lot in the study of magnetism. So in physics, you may see this picture a lot. So this equation is x raised to the 2/3 plus y raised to the 2/3 equal to 1. This is the equation of the asteroid. All right, I have x to the 2/3 plus y to the 2/3 equal to 1. I want to find the derivative, which is a slope at the point x equal to 1 over square root 8 and y equal to 1 over square root 8. All right, what is going to be my answer here? So at the point 1 equal to x equal to 1 over square root 8, y equal to 1 over square root 8, I want to find the slope here, which means I want y prime, right? I need to compute dy by dx at x equal to 1 over square root 8 and y equal to 1 over square root 8. All right, let's do that. So you can see that if you don't know the differentiation, if you don't know the implicit differentiation technique, what you can do is you can say, hey, this is y to the 2/3 equal to 1 minus x to the 2/3, and then you're gonna have y equal to 1 minus x to the 2/3 raised to the 3/2. You can do that too if you want, so you can simplify this thing to an explicit form, and then you differentiate. But it may be harder because sometimes you're gonna get a messy thing on the right hand side. So another way you can do this question is start from here. You can just use implicit differentiation. Implicit diff. So that means you're gonna differentiate the whole equation with respect to x. So you differentiate x to the 2/3, so you get 2/3 x to the 2/3 minus 1, right? This is just a differentiate. And then plus 2/3 y to the 2/3 minus 1. But because y is a function of x, so you have dy by dx with you. And then you're gonna have differentiate 1. What do you get? 0, right? All right, and then after that you have 2/3 x to the negative 1/3 plus 2/3 y to the negative 1/3, and then y prime equal to 0. Seems easy now because you can simplify a little bit. So I am going to move my 2/3 times x to the negative 1/3 to the right hand side. So I have negative 2/3 x to the negative 1/3, and then my 2/3 cancel. So at the end I have y prime. So continue here. So y prime equal to negative x to the 1/3 over y to the negative 1/3, right? So I just copy everything. And then after that, I want y prime at the point x, y equal to 1 over square root 8. Well, which means the answer is going to be negative 1 over square root 8 to the negative 1/3 over 1 over square root 8 to the negative 1/3. Well, which means the answer is, 1 second, need to delete this thing. All right, so this is negative 1 going to be your final answer, right? So I do not need to compute anything because on the top and on the bottom they are the same quantities, right? So we can cancel it and then get 1. So the answer is negative 1. Sounds good. And then it matches with the picture that we have because the slope must be negative and slope is negative 1 as we want. So this is how we use implicit differentiation. So sometimes it is going to be a lot easier compared to you simplify to explicit form. Sometimes simplify to explicit form is easier. Depends on you. So let's do one more example. All right, buddy, let's do one more. All right, so example 46, well, which is the last one for this slides, and then we're gonna move to the next one. Well, we have to download the next one after. All right, so let's look at example 46. Given that y is a function of x, I want to find the equation of the tangent line to the curve here at the point 2, 1. Well, again, you have two ways to do it. First, if you want, you can simplify to y equal to fx and then compute y prime from there. Is it recommended? No. Because if you simplify this thing, hey, how do you simplify that? Because you have y and y to the 4th power, right? Messy. We're not going to do it. So we have better idea. So we're gonna just use the implicit differentiation. So I'm gonna find y prime from implicit differentiation because this is a lot easier, right? So I can start by just looking at my equation, and then, well, I have x squared plus x cubed times y equal to y to the fourth power plus 11. So I'm going to differentiate with respect to x on both sides. All right, I differentiate with respect to x on both sides. So be careful when you differentiate. So differentiate x squared, you get 2x. Differentiate x cubed times y. So here, well, the mistakes start here. Students usually get mistake here. So x cubed times y. This is a product, right? Because you have x cubed and y, which is a function of x. So this is a product. So you have to use a product rule. So to differentiate x cubed times y, so I'm going to get x cubed times y prime, and then plus 3x squared times y. All right. So if you cannot follow me, think again. When you differentiate x cubed times y, right? Oh, different color, please. X cubed times y, right? So here's the thing. So this is a product rule, right? So you have differentiate f times g. So you're gonna have f times g prime plus g times f prime. So that's going to be you whole x cubed, and then you differentiate y, and then add, you differentiate x cubed, and then you whole y. So that is how you get the one that I highlight in blue. And then after that, so on the right hand side, I differentiate y to the fourth power, so I get 4y cubed and then y prime, right? Because by the chain rule, and then differentiate 11, I get 0. So once you have this thing, well, if you want, you can simplify until y prime equal to something good. But I can go faster than that, because all I know is I want slope at x equal to 2, right? Y equal to 1. So that means I can plug in x equal to 2 and y equal to 1 into the equation. So I'm going to plug in x equal to 2 and y equal to 1 into the equation immediately. So I don't have to simplify anything. And then this is 4 plus 8 y prime plus 12 equal to 4 times y prime. Well, which means 4 times y prime equal to negative 16. That means y prime equal to negative 4. All right, so I have y prime equal to negative 4. This is y prime. This is slope at x equal to 2, y equal to 1, right? So the question asks you for the equation of the tangent line. So that means you need to give the equation at the end. So the equation that we want is going to be, remember the formula I just gave you last week, y minus y naught equal to m times x minus x naught. So this is the one that you can use when you want to find the equation of the line. I know that the slope is negative 4 and it passed the point x equal to 2, y equal to 1. All right, so that means y minus 1 equal to negative 4x plus 8, which is y equal to negative 4x plus 9. All right, so this is my final answer. How do you feel? A piece of cake, right? Easy. All right, so that is how we use implicit differentiation. If you have not done it before, so go slow and try to understand this example first. All right, so we are going to move to our next step of the class. So we are going to look at derivatives of trigonometric functions. So you can download the handout from the Blackboard, and the handout is this one. Well, it's going to be part 2. It's going to be part 2, which is start from derivative of trigonometric functions. So we're gonna spend the rest of our time today to talk about derivative of trigonometric functions. All right, so before we head to that, any questions? Any questions for me or any content? So if not, we are going to move to the derivative of trigonometric functions and then inverse trigonometric functions after. All right. Well, I appreciate that you attend the class, everyone here, 36 students. So I know that some of you think that this class is pretty easy. Yes, it is pretty easy. Well, just only before midterm. After midterm, you're gonna learn new things, and it's gonna be a lot harder because you're gonna learn like integration technique or something which is not overlap with your high school content. But before midterm, some of you already did all on high school. So let's think that this is our review, but you know, we have different backgrounds. So we just need to shape everyone into the same way first on before midterm, and then after midterm, when we talk about harder things, so we can go, you know, everyone has the same background. So let's look at derivative of trigonometric and inverse trigonometric functions. So we're gonna start by looking at the function sine, fx equal to sine x. So the function sine here is the one that I just graphed in blue, like blue here. So as I told you on the last chapter that the function sine lies between -1 and 1. So the value of sine cannot greater than 1 and cannot be below 1. So if you look at the peak of the sine graph and you're trying to find the derivative, so the derivative means the slope of the tangent line, right? So that means, well, at this point, the one that I just dot in red, so this is the peak of the sine graph. And then if you find the slope of the tangent line, it's going to be the horizontal line, right? Because this is the tangent line that you have. Well, which means the slope of the tangent line is 0, right? The slope of the horizontal line, this is going to be 0, which means at this point, the derivative of f is going to be 0. Well, the same thing at the peak here. So you're gonna get that the slope is equal to 0. Interesting, right? And then at the point that function sine gives you 0, well, if you're trying to find the slope of the tangent line, you can see that at this point, the slope just go perfect as a -1, right? So you can match with your derivative graph, and then you can see, hey, the slope is -1. Interesting. So which means if you complete the graph of derivative here, so it seems like if you have fx equal to sine x, when you take derivative, look like you get cosine x because the graph looks similar to cosine. Is it true? So we're gonna look at the proof. So we're gonna prove you that the derivative of sine is equal to cosine. And then we can build another formula after that. So let's look at the proof first. So if I have the function sine x, well, how do I know that differentiate sine get cosine? So for sure, I can use the definition. So by using the definition of derivatives here, well, for now, everyone should be comfortable to compute the derivatives by using definition. Well, I told you so many times it will be on the exam, and don't cry if I ask you to find derivative by using definition and you don't know how to do it because you only know the formula. So the definition, you use this thing. So I can use fx plus h minus fx over h, right? Where h goes to 0. And then after that, I replace f x plus h to sine function. And then after that, well, I have sine x plus h. So by using the trigonometric identities, so I am going to expand that and get this, right? And then, well, I simplify everything. So the step here, I'm not going to read it for you. You can follow this thing easily. So nothing other than algebra, right? So you just use algebra to simplify. And then you want to simplify everything, you're gonna see that you end up with 4 terms, which is 1, 2, 3, and 4. Well, you simplify everything, so you get this. The one that I am going to highlight in yellow here, so those are easy because limit of sine x where h goes to 0. So this is going to be sine x because, well, when you take limit, when h go to 0, sine x is just constant, right? So just sine x. And then also when you take limit of cosine x where h go to 0, this is just cosine x because, you know, cosine x is constant in terms of this limit. So what you need to figure out is limit of sine h over h and limit of cosine h minus 1 over h. Well, in the book you have the proof of limit of sine h over h equal to 1. Well, for those of you who are interested, you can look at the proof by yourself. So I'm not going to go over the proof here because we have limited time, but I will tell you the idea. So in the book, we have that limit of sine theta over theta where theta goes to 0. This is 1. If you read the textbook that I attached in Blackboard, you're gonna see that the proof start from, they consider that the line that I highlight in yellow here is less than the line that I highlight in green, and then less than the line that I highlight in, and bigger than the line that I highlight in blue. And then when they have these 3 lines, so they compare it, and then they use squeeze theorem. And then after that, they use squeeze theorem, so they can prove that limit of sine x over x equal to 1, where x go to 0. That is how we prove equation 2 here. But as I told you, I'm not going to spend more time to explain the proof. Well, if you feel like you want to learn the proof, so you can, well, email me maybe so I can explain you outside the class. So, and then after that, we continue from limit sine x over x, so we get limit cosine x minus 1 over x equal to 0 as well. So this is, you know, the theory that we obtained from the previous one. All right, and then after that, once we have those two, so we can plug into our equation before, and we're gonna get that f prime x equal to cosine x. This proves that. So the bottom line is, this proves that if you start from sine x and you differentiate, so you get cosine x. Good. It looks good, right? Differentiate sine, you get cosine. All right. So, well, before we move to another function, so let's look at what we got from that little theorem. From our little theorem, we know that limit of sine x over x equal to 1, where x go to 0, right? So from here, you can use this fact to solve some limit problems. So for example, if I want to find limit of sine 7x over 4x here, so I can simplify my sine 7x over 4x to 7 over 4 sine 7x over 7x. Well, I can simplify like that. And then I know that this thing gonna goes to 0. The one that I bracket in red, it's gonna go to 1. Because if I consider limit of 7x, limit of sine 7x over 7x, where x go to 0. So if x go to 0, 7x gonna go to 0 as well, and that means I have limit of sine something over that thing go to 0. Well, it matches with the form I have, so this is also 1. So once you simplify that, so the thing that I circle in red gonna go to 1, and that means your answer is 7/4 because you have constant 7/4 left, right? Does it make sense? This is how we can, use the little theorem that we know to solve some limit problems. For example, on the previous exam, like last year, I used to ask limit sine x minus 2 over x squared minus 4, where x go to 2. This thing is not hard, so if you feel like you want to do this thing, you can say that, hey, this is sine of x minus 2, and you factor x squared minus 4 to x minus 2 and x plus 2, right? And then if you observe, you're going to see that this, right, sine x minus 2 over x minus 2. So you can think of this thing going to be limit of sine x minus 2 over x minus 2, where x go to 2, times limit x go to 2, where 1 times x plus 2, right? So I split to 2 pieces, and then you can see that on the first pieces, so when x go to 2, that means x minus 2 go to 0, the same thing, right? And then you have x minus 2 go to 0, sine of x minus 2 over x minus 2, this is 1. Because you know that is 1 from the little theorem that we just did on the previous slide. And then the remaining term you have 1/4. This is going to be a quarter as your answer. This is a short question that I asked, I think 2 years ago or something, on the, when I taught American students there when I was a PhD student. So, and some students just miss this question because, well, they don't understand the concept of limit sine x over x. So make sure that when you see limit sine of anything over that thing, when that thing goes to 0, it's going to be 1 all the time. So, all right. So next, so this is just the, the corollary that we have on this slide. So let's come back to the derivative part. So we already did that. If you have sine x, you differentiate, you get cosine x. Now, we have a set of formula here. So if you differentiate sine, you get cosine. On the other hand, if you differentiate cosine, you get negative sine. If you differentiate tan, you get secant square. If you differentiate cosec, let's start by cotan. If you differentiate cotan, you get negative cosec square. And then if you differentiate cosec, you get negative cosec cot. If you differentiate sec, you get sec tan. Well, some of you gonna ask me that, do we need to memorize this thing? Do we need to memorize? Well, the answer is yes. Because on the exam, this is not given. So you have to memorize it. And well, we have technique to memorize it. So if you did, well, if I were you, I am going to memorize differentiate sine equal to cosine first, differentiate tan equal to secant square, and differentiate sec equal to sec tan. And then you can see that another 3 formula. So they use the same pattern. So if you differentiate cosine, so the answer is sine. This is just a co-function of cosine, right? And then you just add the negative sign to it. So the same thing with differentiate cotan. So the answer gonna be, well, for differentiate tan, you get secant. And then if you want to differentiate cotan, so that means you need to get co-function of secant, which is cosec, right? And then you just change the sec to cosec, and then you add negative sign. So the bottom line is, no matter what, you need to memorize this thing, because we're going to ask you to differentiate. And if you cannot remember the formula, you're going to waste your time on the exam to prove the formula, right? Because let's say that I don't know, I cannot remember the formula of tangent, differentiate tangent. So on the exam, I may need to just start by using the definition and prove the formula of tangent. Will waste my time, because, well, I believe that eventually if you do the exercise again and again and again, you're going to absorb this thing and then you're going to memorize this thing. So we just need this 6 formula. So the one that we're going to use a lot is going to be the one that I box it. All right. So this is the trick that you can use to memorize. All right. So let's look at example. So I'm going to show you how to use the formula to differentiate. All right, so let's start by example 48. All right, so let's do this together. So example 48, I want you to find dy by dx from the given equation. All right, so first of all, I have y equal to cosine 3x times tan x squared. Whoa, I told you this is basic question. All right, this is not hard at all. So I have cosine 3x, which is our first function, multiply with the second function here. So if you want to differentiate, of course, y prime, so you need to use the product rule. So this is going to be, I keep cosine 3x, and then I need to differentiate tan x squared. And then plus, I keep tan x squared. And then I need to differentiate cosine 3x. Right? So now cosine 3x is done. So I need to differentiate tan of x squared by the chain rule. So I'm going to get secant square of x squared and then multiply to x, right? Because by the chain rule, the function tan x squared, this is tan of x squared. So I differentiate tan first, so I get secant square. And then I need to differentiate inner function. That means I need 2x. Well, if you are not ready to go fast, just go slow, right? So you just write all step first. Well, but if you feel like, hey, I can go faster than this, you can skip some step, but make sure that don't skip too much. Well, I guarantee that if you show your work as I show on the slide here, so you're gonna get full credit on the exam for sure, because this is good enough for the exam. But if you skip more step, well, maybe you're gonna lose the point because we cannot follow you. So plus tan x squared, and then for cosine 3x, so I am going to differentiate cosine first, so I get negative sine 3x, and then I need to differentiate my 3x again because that is my inner function, so I get 3. Well, I stop here immediately because I don't want to simplify, because if I simplify, I may get it wrong, right? But well, for those of you who want to challenge yourself, you can simplify. So I can get 2x cosine 3x times secant square x squared, and then minus 3 times tan x squared sine 3x. Well, I told you again, it doesn't matter if you simplify or not. Well, the line before, it is acceptable to stop at that line. But if you want to simplify, you can. All right, so next, we are going to look at 48.2. So I have y equal to 1 plus secant x cubed raised to the a quarter power. So here, what I'm going to do, I am going to differentiate it. So of course, chain rule, right? So I'm going to do a quarter, and then that function. All right, this is my inner function to the 1/4 minus 1. All right, this is my inner function, and that is differentiate inner function. All right, you see, I go slow all the time, and then well, that will reduce your chance to get a mistake. And then a quarter, and then this thing is going to be 1 plus secant x cubed, and then this is negative 3 over 4, right? And stop there. I'm not going to touch anything. So after that, I differentiate 1, I get 0. Right? I differentiate secant, I get 10. Oops, sorry. I differentiate secant, I get secant and tangent. Well, you need to memorize the formula first. Differentiate secant, so you get secant. And then after that, by the chain rule, I have 3x squared with me because I need that thing too. All right, so done. I'm done. That's it. Right? Good enough. Well, again, if you want to simplify, you can simplify, but well, I'm done because I don't want to simplify more because, well, it may get me to a mistake or something. All right, sounds good. So any questions so far about differentiation using trigonometric functions? So this is your first day for differentiation with trigonometric functions. So it may be a little bit hard for you because you have not memorized this formula. But once the times go by, I guarantee that you're going to get better and better, because once you memorize the formula, you are going good and good and good. All right, so we have, I think, 2 more examples before inverse trigonometry, and then we can stop after inverse trigonometry. All right, so let's do example 49. So let's practice the chain rule. This is the one that this is not the O exam for engineering student, but this is the O exam for science students. But well, they are similar, so you can practice this thing as well. So let's look at this question. So let's start by I have y equal to f of this function, and then I have f prime 0 equal to pi over 4. I want you to calculate dy by dx, where x equal to pi over 2. Well, doesn't look hard to me. So let's start by you looking at y, right? And you know that y is a function of that thing. Well, I am going to replace this thing by u. So this is y is a function of u. Right? So I'm gonna start by let my u to be x squared times cot x. Well, and then my u gonna be a function of x, right? So now if I want to differentiate y with respect to x, I can differentiate y via u and then u by x. So that means then if I want to differentiate dy by dx, right? So I can differentiate y with respect to u first, and then differentiate u with respect to x, right? And then dy by du, the notation is f prime u. Easy. And then du by dx, hey, I know that u is x squared cot x, so why don't I differentiate, right? So I'm gonna do it here. So my du over dx, so I have to differentiate x squared times cosine x. Well, product rule for sure. So I have x squared differentiate cot, and then plus cot differentiate x squared. All right, so I have x squared times negative cosec x squared. And then, well, this is a formula of cosine x, differentiate cosine x. And then I have cosine x times 2x. All right, sounds good. Well, that means here I have f prime u times negative x squared cosec square x, and then plus 2x times cotangent of x, right? So I just copy everything here. Simple. And then after that, I evaluate at x equal to pi over 2. So well, you have to think a little bit. When x equal to pi over 2, what is your u? So when x equal to pi over 2, so your u gonna be x squared times cot x, which is going to be pi over 2 square times cotangent pi over 2. And if you don't know, cotangent pi over 2 is 0, right? Because, is that right? Cotangent is cotangent is cos over sine. Well, that means this is 0 over 1, and that is 0. So this is 0. So that means when x equal to pi over 2, u equal to 0. So, well, when I compute this thing, so I have f prime 0 times negative, well, x equal to pi over 2 cosec square pi over 2 plus 2 times pi over 2 cotangent pi over 2. All right, it is easy enough because cotangent pi over 2 is 0. Good. And then cosec pi over 2 is what? What is cosec pi over 2? Anyone know cosec pi over 2? This is 1 over sine pi over 2, right? And sine pi over 2 is 1. So that is 1. So this is 1. And then, well, let's compute that thing. So f prime 0, this is pi over 4, right? F prime 0 is pi over 4. And then I have negative pi over 4 square over 4 times 1 plus 0. So at the end, if I simplify, sounds good? Well, any questions? I know it's 50 minutes already, so you are a bit tired, but well, let's stay with me about 20 minutes more. So, all right, so this is the last one for trigonometric function, and we're going to move to inverse trigonometric function, and then we are happy for today. All right, so example 50, let's try to find dy by dx again. This time I want you to compute dy by dx by using implicit differentiation. You can see that it is impossible that you're going to simplify to y equal to fx, right? Because you have sine y here. If you simplify, so you're going to get arc sine at some point, and then you also have xy squared. How could you do that? So no way. So we're going to use the implicit differentiation. All right, so let's look at this question. All right, so start from, well, this should be a quick one. So I am going to differentiate both sides with respect to x, right? And then after that, so let's look at how it's worked. So on the left hand side, differentiate x squared, so you get 2x. So differentiate sine y, so I get differentiate sine, I get cosine. However, y is a function of x, so I have y prime, right, by the chain rule. And then plus xy squared, again, I have to use product rule. So let's delete this thing. And I have to use product rule here. So I differentiate xy squared, so I get x times 2y, y prime. And then plus y squared, right? So this is how I differentiate by using the product rule. And then on the right hand side, I get 0. All right, sounds good. And then after that, I can simplify a little bit because I want to solve for dy by dx. So I'm gonna save my y prime on the left, and then move everything else to the right. So I'm going to have negative cosine y times y prime, and then plus 2xy times y prime, and then equal to negative 2x negative y squared. So I move everything I do not want to see to the right hand side, and then after that I factor, right, almost there, and then well, I have y prime equal to negative 2x minus y squared over negative cosine y plus 2xy. I'm not going to simplify more, so that's my final answer. See, this is pretty simple and easy, right? All right, so let's move to derivative of inverse trigonometric functions. So for those of you who still in, so type check in the chat so I know that you are in for today. So, all right, please do so I know who attend the class today. So, all right, so the last topic for today, this is going to be derivative of inverse trigonometric function. So let me see, we have few examples. Whoa, we should be on time. Even very good. All right, any questions, anyone? So 15 minutes more, and then we should be good for this topic. All right, so derivative of inverse trigonometric functions. So I know that for some of you, inverse trigonometric is a pain. So you hate it. I hate it too. But well, let's see how we develop the formula for inverse trigonometric differentiation. So let's start by y equal to arc sine x. So to avoid the confusion, so we are going to say that we use the notation y equal to arc sine x, not y equal to sine inverse x. So if you use this notation, well, let's avoid that for this class, because it is also correct, but I mean, some of you understand that sine raised to the negative 1, this is 1 over sine. That's not correct. 1 over sine is cosec. Well, to make sure that this is inverse, so we're going to use arc sine for this class. So we're not going to use sine raised to the negative 1. Just avoid that notation to avoid the confusion. So we're going to use sine x all the time. So when we say y equal to arc sine x, that means x equal to sine y. Right? This is the same thing. This is the inverse, right? So you swap the notation x and y, right? And then that's it's how to find the inverse. So well, if I start from y equal to arc sine x, so let's see. So I have sine y equal to x, right? And then well, if I have sine y equal to x, what does it mean? So it means that well, if I have y here and then sine y equal to x, that means the opposite side is going to be x. The opposite side of y is going to be x, and the hypotenuse is going to be 1, right? Because you know that your sine function, this is going to be your opposite over hypotenuse, right? In Thai, it's going to be likeข้ามฉากor something. Cannot remember, but well, I have x1 here, and then this is going to be square root 1 minus x squared by Pythagorean theorem, right? By Pythagorean theorem. So you're gonna have that the remaining side is going to be negative square root 1 minus x squared, and then that will leave you cosine y equal to negative square root 1 minus x squared. And then now once you have that, so keep it to use it for later. So when you have sine y equal to x, you differentiate by using the implicit differentiation. So you're gonna get cosine y dy by dx equal to 1. And then you simplify, so you get dy by dx equal to 1 over cosine y, which is 1 over square root 1 minus x squared. And this is the formula for differentiate arc sine. So differentiate arc sine, you get 1 over square root 1 minus x squared. Well, where x less than or equal to 1, or where absolute x less than or equal to 1. Well, this is a formula that you have to memorize. But you know what? If you happen that you forget the formula, so you can start by what I just did here. So I know that memorize the formula is a pain, but well, every time I forgot the formula about inverse trigonometric function, I start from the base again. So I start from y equal to sine x, and then I use implicit differentiation to find the formula of arc sine. Well, if you can do this thing, you will not forget inverse trigonometric function. Trust me, I mean, well, I can memorize it because I teach it every day, but for you, it's gonna be a lot harder because you have a lot of things to memorize. But well, as I told you, if you happen to forget it, like on the exam, just something happened and you cannot remember, well, you can always start deriving the formula again by using the basic sine and cosine function. Well, this is what I told students when I teach derivative of inverse trigonometric function, because students always complain that a lot of formula to memorize, but well, if you know the root of the formula, it's going to be super easy to memorize it. And then here, if you want to memorize, yes, you can. If you forgot it, well, that's not a big deal because we can start from the base and just build up the formula again. That makes sense. So we're gonna do the same thing with arc cos, arc tan, arc sec, and every trigonometric function. So this is how you prove arc tan, and also arc cos is the same. So everything you start from, let's say y equal to arc tan x. So I say this is tan x equal to y, and then I use the implicit differentiation. Well, at the end I get 1 plus x squared. 1 over 1 plus x squared. So this is my formula for differentiate arctan. Like, so it's pretty simple to me, but well, hopefully you see the point that I just mentioned. All right, so let's look at example. So to sum up, so your formula is dip arc sine. You're gonna get 1 over square root 1 minus x squared. Differentiate arc cos. So you get the same thing, but just negative sign. So differentiate arctan. So you get 1 over 1 minus x squared. Well, differentiate arccot, which is a co-function of arctan. So you get the same thing with arctan, but you just add negative sign. So the same thing with arcsec and cosec. So arcsec, you get that. Arccosec, you get negative sign of it. So the same thing with trigonometric function. If you can memorize arc sine, arctan, and arcsec, so the arc cosec, arc cot, and arc cos is going to be easy. You just add the negative sign. And you know what? It is critical that you have to memorize this thing, because when we integrate in the next few weeks, when we integrate, if you see integrate 1 over square root 9 minus x squared, well, it's going to come back to arc sine because it looks similar to this thing. So we can match with arc sine and just come back to arc sine at some point. So if you memorize this thing just one time, when you integrate, it's going to be easy for you because you already memorize all formula from derivatives, and integration is just, you know, the operator that's opposite to differentiation. All right, so we're going to wrap up today by doing 2 examples, and that is for today. All right, so example 51 and 52 for today. All right, so should be about 10 minutes to finish this 2 examples. So let's do it together. All right, almost there, everyone, just a bit more. All right, so let's start by looking at example 51. So we're gonna practice how to differentiate using the inverse trigonometric function. So I wanna differentiate this thing for sure. This is product rule. So I have to do y prime equal to x cubed, right? And then I differentiate arc sine 2 plus x, and then plus I do not need to differentiate arc sine, and then I differentiate x cubed. All right, this is 1 over square root 1 minus 2 plus x squared, right? By using the chain rule. And then I need to differentiate inner function, which I need to differentiate 2 plus x as well. And then arc sine, this is good, so I don't need to differentiate. And then differentiate x cubed, I get 3x squared. All right. However, differentiate 2 plus x is 1, right? So 1 multiply anything is 1, so good, I'm done. Simple, right? Pretty simple. This is a piece of cake, right? This is super easy. All right. Next. So I look so happy because it's almost, well, I like differentiate because this is super easy. All right. So y equal to cosine of arctan square root x. So again, you use the chain rule here. So the outer function is cosine. So you differentiate cosine first, you get negative sine. Right? And then for sure, you need to differentiate arctan root x here because this is your inner function. And then you, one more time, you differentiate arctan. So you get 1 over 1 plus square root x squared. And then you have to differentiate inner function, square root x. So if you can memorize the formula of arctan, the differentiate arctan x is 1 plus 1 over 1 plus x squared. So that's how I differentiate using chain rule here. And then the last step is what is, well, I am not going to simplify anything. So differentiate square root x, so I get 1 over 2 square root x. Well, you can try it. So simple and easy, everyone. All right. Any questions this slide? Sounds good. Well, if you feel like I go too fast, so you can talk to me after class or something, because, well, I think this is acceptable because you already know the chain rule and we just add more formula for you. All right, the last example for today is 52. This is our O exams, and this is considered as the medium one. Well, not that hard, but the thing is that you need to use the implicit differentiation with this term. So let's complete this thing and, well, we are good to go. All right, so let's try together. So first, of course, when you see this thing, you need to use implicit differentiation because the given equation is of this form. So you have no way to simplify to y equal to something. It's impossible. So we're gonna start by differentiate both sides. All right, and then equal to differentiate that side arc sec 3x plus 2. All right. Next, what else? So what we can do is we differentiate x squared, right? So we differentiate x squared, you get 1/2. You differentiate arctan, so you get 1 over 1 plus y prime, y square, and then you have to differentiate your inner function, which is y squared. All right, so if you cannot follow me, so think, if I want to differentiate arctan x, arctan something in the rectangle, so that's going to be 1 plus 1 rectangle square, right? Which means if I wanna differentiate, if I wanna differentiate arctan y square here, so the y square is in my rectangle here, so I just add y squared there. So I need to differentiate y squared after as well. And next we do on the right hand side. So we are going to have differentiate arcsec. So you get 1 over absolute value of 3x plus 2 square root. If you remember the formula of arcsec, so it's going to be 3x plus 2 square minus 1. And then times the inner function, differentiate inner function. So the formula for differentiate arcsec, this is 1 over absolute value of x, absolute value of that rectangle, and then square root rectangle square minus 1. Well, spend your time to memorize it, and then, well, you will get better. Next, well, here I can simplify that thing more. So it's simply 1 over 1 plus y to the 4th power. Here I get 2y prime, right, by the chain rule. And then that I have 1 over 3x plus 2 square root 3x plus 2 square minus 1. And then this is 3 because I differentiate 3x plus 2. Well, now I plugging in x equal to 0 and y equal to the 4th root of 3, right? So I have 1/2 plus 1 over 1 plus 3, right? Because I plug in the 4th root of 3 and then I raise to the 4th power, so I get 3. And that is 2 times the 4th root of 3. And then y prime, this is what I want to solve. And then equal to 1 over 3 here, because I plug in x equal to 0. And then here is 2 square minus 1. Oh, that's 2, sorry, that's 2. And then 3 here. So after I simplify this thing, so I'm going to have y prime equal to square root 3 minus 1 over the cube root, the 4th root of 3. Well, you can do that by yourself because this is just the algebra. That's it. Right? If you just, oh, I need to delete this thing. So 2. Well, not that hard, but use the idea of implicit differentiation as well. Usually students gonna make mistake on this step that I highlight in light blue because you forgot that you have to use implicit differentiation technique, the chain rule inside there. And also you forgot the absolute value here. That's usually your mistake on the exam. All right. So we are going to stop here for today. So the last thing I'm going to answer some people in the chat. We expect to remember for sec, cosec, and cot too. Yes. So you have to memorize everything, but you know, sec, cosec, and cot, we don't use it often compared to sine, cosine, and tangent. But you have to memorize as well, just in case you see it. All right, so check out. Good. All right, any questions? So if you don't have questions, you can leave now. So thank you for coming today. Well, you can open the microphone and say hi to me too if you want, but all right, thank you. So we're gonna see you again on Wednesday. So at that point, we're gonna start differentials.